Welcome back. Today I am going to talk about PID nominal control. I have received a lot of requests through emails or some other ways that I should make a video with adaptive control having a PID baseline or nominal control. So here it is, this is that video. First of all, in the previous video, we covered adaptive control with integral nominal control, and in industrial applications, the content of the previous video is more important in my opinion because that's how or many other people, I don't want to say many other people uses in industrial applications. But PID control, for example, in my lab, when we purchase an off-the-shelf quadcopter or some aerial platform or some ground vehicle, they come with already tuned PID gains, PID controllers. And on top of their existing PID nominal control, we insert adaptive control. So we also use PID as a nominal control as well. And PID is so popular method that also gives some level of robustness to uncertainties. So let's use PID nominal control with adaptation. All right, this video starts like the previous video in our adaptive control and learning playlist so far. For adaptive control, neuroadaptive control, performance recovery, and all other videos, we use this feedback, feed-forward method. And in the previous video, we covered, we changed this nominal control to integral nominal control, which is similar to PI. And now we are going to add the derivative term, PID, and to be self-contained, I am going to show you all the details, all the steps, and how you can use a PID controller as the baseline or nominal control. All right. We look at this system similar to previous videos. X is measurable, A, B are known and controllable. Control effectiveness uncertainty, lambda is positive definite with diagonal elements. And we are going to look at, in this video, structured uncertainty. I will give a comment similar to my comment in the previous video. Guys, we are just changing the nominal control. So all the principles and steps you are going to learn in this video, you can apply to neuroadaptive control and all other videos, okay? All the fundamentals will remain the same. All right, to summarize, the goal of this lecture is to show that you can use other types of nominal controllers, and in particular PID with adaptive control. And if you look at the literature, PID has different structures, although at the higher level, they all look more or less the same. I am going to focus on a widely adopted popular form of PID nominal control, which looks like this. There exists a matrix that multiplies y minus c. This is the position gain. Right, we are dealing with y can be 2-3 dimensional in general. So I don't want to say this is a gain. It is not a scalar. It is basically, it may not be scalar. That's my point. But without loss of generality, let me refer to it as the position term, integral term, and the derivative term. And y is basically a minus x. For example, if your state includes position and velocity of cart, then you can select e to be 1, 0, so that y becomes p, so that you would like to derive position state to the command. This is if this was your command following objective. So here e allows us to select a subset of states for command following purposes. All right, here is the PID. So similar to the previous video, I am going to provide step-by-step guidance how you can use PID as your nominal control. All right, the first step is identical to the step that I covered in the previous video as well as in some of the other videos in this playlist. So I am going to insert u, which is un plus ua. This is the uncertainty. In the next step, I am going to add and subtract bun minus bun. Then I am going to send this guy inside. After that, I am going to do some grouping. I group these terms like this, and taking this term and this term together, I basically this plus this is equivalent to this W transpose theta form. Basically, I did this grouping to collect all the unknown weights here and create theta of x. And step number 1 allows you to write certain part or known part of the system and uncertain or unknown part of the system. So we kind of separate the system into 2 parts. Now this brings us to step number 2. In step number 2, we are going to choose PID, K1, K2, and K3 gains based on the certain part of the system. Because don't forget, nominal control defines the ideal system behavior in the absence of uncertainties. So pretend like you don't have anything here. You have this system and you want to choose K1, K2, and K3 to stabilize this system and achieve a desired level of command following performance. Now, I have covered PID and examples of PID in another playlist called Lectures on Control Systems. And this basically PID and PID examples covers advantages and disadvantages of PID control, and then provide several examples in the second video. And I am in this video, I am not going to discuss how to tune a PID control, but if you would like to refresh your mind, I strongly suggest that you go and watch these 2 videos on the Lectures on Control Systems playlist, so that given a system like this, you will be able to tune K1, K2, and K3. All right. And in addition to X dot, we also have Z dot. We no longer have one ordinary differential equation or one system. X dot is coupled with Z dot. Why? Because in coding or in analyzing, it is easier to deal with derivatives. So we have an integral. I am going to call this integral Z. In other words, Z equals the integral y minus c. Then to get rid of the integral, I am differentiating z with respect to time. So we have z that equals to y minus c or ex minus c, so that we can write the nominal controller like this. After step 2, this is a little bit involved, but bear with me. This is not that hard to understand. So once you plug your nominal controller here, right, you are going to have an x dot here and here. So you need to solve this for x dot. And here we are dealing with matrices, so you need to be super careful with your math. So first of all, x dot here, I am going to send it to the left side of the equation. So if you look at b minus k3e, is multiplied by x dot. So I am sending it to the left hand side. We have identity coming from x dot here plus b k3ae. And f needs to be invertible. It is hard to find a case which is not invertible. Of course, you can mathematically construct one, but in practice, it is very hard to encounter if you are designing PID gains, as I explained on the 2 videos that I referred on the previous slide. I am going to call this matrix as F in order to simplify the following steps. I am going to call this matrix G, which is obtained using AX, B, K1, and when you expand the rest of the terms, they appear here. This portion is similar to here. Now, x dot, if you multiply the left and right sides of this bigger equation with f inverse, you have x dot equals to f inverse gx, f inverse bk1, and all these terms. So since the motion of the system is now depending on x dot and z dot, I would like to write them together in one aggregated or compact state space form. I am defining Kc to be x and z, and Kc dot becomes f inverse multiplied by x, this multiplied by z. These terms are coming from basically, right? This term is coming from here, this term is coming from here, E is coming from here. You can pause the video and look at the details, but at the end of the day, you have AR, BR, and aggregated ABA matrix, including F inverse B and 0, and here is the uncertainty. Now, in the absence of uncertainties, this portion of the system defines your ideal behavior. Okay, for this purpose, we are going to define the reference model like this. Basically, Kc R dot equals to AR Kc R BRC. But before going to that, let's select UA to be W minus W hat transpose multiplied by the known basis function. And you arrive Kc dot equals to AR Kc, BRC, BA, and the rest are the adaptation related terms. Once again, this portion defines the ideal behavior in the absence of adaptation and uncertainties. So this is your reference model. Finally, in step number 4, we are constructing the error dynamics, defining the error between Kc and Kcr, and we already defined W tilde to be W hat minus W. We arrive this E dot dynamics. So this E dot equals to AR E minus BA, and the rest is exactly similar to the what we have seen in adaptive control high order case video. Only B is replaced with BA. So if you, for example, consider this Lyapunov function candidate, PE gamma inverse trace W tilde transpose W tilde lambda, you are going to get B dot minus E transpose RE, and then you apply Barbalat to show error going to 0, and this will be your weight update law, this will be your Lyapunov equation, gamma is positive, R is positive definite. If you haven't watched this video, I strongly suggest that you watch it first to understand the similarity. In fact, if you are serious about adaptive control, you should have watched all the videos in the order that I post in the playlist of lectures on adaptive control and learning. All right, all done with the theory. Let's do a Matlab example. Similar to the previous video or similar to the adaptive control example high order case video, I am going to consider mass spring damper system. The first state is the position, the second one is the velocity. I am going to assume I know nothing about this system. I don't know mass, I don't know spring constant, and I don't know beta damper constant. In this case, state space matrices A and B has this empty looking form. Mass appears in the control effectiveness uncertainty, and alpha and beta appears in this W0 transpose theta 0. And it depends on velocity, I assume. For simulation purposes, is P dot to the power of 3 proportional. And how we come up with this state space representation, to understand that, I encourage you to watch this video and this video, and you will get a deeper understanding of this example. But I will pretend like you already watched these two videos, so I am going to jump start with this example, Matlab example. All right, so in this example, A and B are given from the state space, actually nothing known about the system, so we have this empty looking canonical form. And we are going to choose E to be 1, 0, because 1 represents the first state, right? You have Y equals to EX if you choose this to be like this. You have 1, 0 multiplied by p dot or x1, x2. So you end up having p. We would like to regulate position. We want position state to approach to given position, comment C. So to summarize, the adaptive control with model reference adaptive control with PID nominal control, you have this UN nominal control signal, and you have theta of x. Theta of x includes not only the original structured basis function, but also nominal control because of the lambda. Y dot encoding, or in general, right, in industry, Y can contain measurement noise. So practically speaking, we would like to use a filtered Y dot. For example, instead of using Y dot, we are going to use this filtered derivative YD or YFD, you can name it, which is Y dot, right, in Laplace domain, YS means Y dot in the time domain. And this Y dot is filtered through this 1 over lambda inverse S plus 1 low pass filter. So this is the low pass filtered Y dot. It is very meaningful to use that one instead of actual Y dot. If you look at this side, this is equivalent to this, but this is the state space representation. You can take the inverse Laplace transformation, you arrive to this filter form. In state space, you have basically q dot equals to minus lambda q minus y, and filtered derivative is minus lambda q minus y. And in real world applications, I tend to choose lambda between 10 to the 40, 10 to the 50, 10 to the 60, which should be more than sufficient. Sometimes you can also use second order filters. That's also fine. Sometimes I use second order filters as well. This is the first order filter, right? All right, so the remainder of the algorithm summary is Ex minus C, which is Z dot, the integral term. W hat estimate, Kc minus Kcr. Kc is not only X, but now including Z. BA, F inverse B, and 0. And again, I defined F here. I want this control algorithm summary to be compact for your eyes. And this is the reference model. I included AR and BR. I am going to choose K1 to be 4, K2 to be 0.5, and K3 to be 2.5, which makes AR Hurwitz. AR needs to be Hurwitz. That's something you should check. Again, I covered how to tune K1, K2, and K3 in these PID, tool with PID videos I referred earlier in this lecture. Basically, you should watch them, and how you choose these PID gains are important in practice. All right, here there is nothing different than the previous videos. Cleaning routine, discretization, and first order Euler's Euler methods discretization. Mass spring damper, A and B matrices, lambda here, W0, initial condition for states. This is, again, you can code it by yourself. You can play with K1, K2, K3, proportional, integral, and derivative gains. In this example, since we only have one output, they are scalars. This is E. This is a little bit, this lambda is different than that lambda. This lambda here, the second one, is the filter constant when you obtain YD filtered derivative of Y. So please don't get yourself confused. And the remaining is F, G, B, A, R, B, R that you are going to need for the code. Gamma, P, W hat. This is Y. This is Q. This is the filtered derivative. This is UN, integral state, adaptive control. Total control is UN plus UA. And this is the Kc XZ. This is the aggregated reference model, W hat, and finally applying to the state, system dynamics. The data recording and plotting routines of the code, again, you should code it yourself. I am not going to explain these plotting routines, just take the screenshot, code it yourself, and put them, these 1, 2, and 3 into the same Matlab code, so that you can, and then click run them. All right, here are the results. So when you turn off the adaptation, if you would like to control the system with only the nominal controller, here is what you get. Yellow is the command, position command. Blue is the ideal reference model behavior for position, and black line is the actual position, so X1. Same for here, this is the reference models, blue is the reference models, reference model history, and black is the actual velocity. This is the control signal. So PID control, basically, because of the uncertainties, the system could not able to behave as the reference model behavior. So when we turn on the adaptation, system nicely approaches to the ideal reference model position, and adaptation cancels the effect of the uncertainties so that PID can do its job. All right, so I hope you enjoyed this example. Again, code it yourself, try for different adaptation gains, PID gains, and enjoy, just try to have fun. I would like to conclude this video how I concluded the previous video. This paper published in International Journal of System Science, I believe this is a very important paper, not because I wrote it, okay, but this is with collaboration with Air Force as well. And for certain systems, we would like to have different nominal controllers. And for certain systems, we have more nonlinear systems. What I mean by that, right? I mean, yes, the delta uncertainty is nonlinear, but sometimes instead of AX, we have f of x. And these nonlinearities sometimes helpful that we don't want to cancel their effect. So understanding especially sections 2, 3, 4 of this paper published in 2020 will help you to apply model reference adaptive control concepts to nonlinear systems, allow you to use nonlinear reference models in adaptive control. And because, you know, maybe you would like to enforce state constraints, some control, and reference models behaviors can be limited up to a region, but you may want to explore, for example, nonlinear velocity damping effects to better control the damping of your reference model. In this case, reference model will become nonlinear, and simply you may want to use nonlinear nominal controllers like sliding mode in adaptive control. So understanding sections 2, 3, 4 of this paper will help you to achieve these objectives here. And right now, I convince you, if you watch all the videos on this playlist up to this level, you should be able to easily understand this paper, because in this paper, I am using more or less the same terminology. It is written by me, so it is my style. You are going to see the style in these videos so that you can better or much easier understand that content. And if you have any questions, you can post here, you can send me an email. If you like these videos, subscribe to the channel, give a like, and we can go from there. All right, thanks, take care.